my cousin various other notions of bounded cohomology or epsilon representations and stuff like that. But this is an algebraic notion, and this can describe this theorem as a calculation in this world. So suppose you have suppose M will be an abelian group with a filtration. So I have the sequence of group Mi, which are rising up to M, and they satisfy these not sequence of sets, so Mi are subsets. They're not groups. Mi are subsets that are going up to M, and they satisfy this condition that Mi plus Mj is in MCij. There is some constant Cij such that if I look at Mi plus Mj, then I don't run away. Okay? Melanie, are you happy? You like kind of no? Okay. Okay. So I have this collection of sets. So in our case, this would be this M would be MD, so these would be the D polynomials, and I would be taking this filtration by rank. Okay. Okay. So I have this. Right. So I can define what is in and I have a G action. So I have G acting on M. G is some abelian group. Okay, so that will be our G over there, and we will be looking at the trivial action, but the general question would be for any G action, and you can define this notion of so what would be an approximate cocycle. So we say that rho is an approximate cocycle. If the boundary map, if the image of, I'll write this for our case in a minute, but if the image of the boundary map is inside Mi for some I, okay, I'll say that rho is an approximate cocycle. Well, if it were a true cocycle, then the image of the boundary map would be 0. So it would be an approximate cocycle if the image of the boundary map is in one of these filtered groups. So this would mean, in our case, let me just say, so in our case, or for n equals 1, an approximate, maybe I should say that, an approximate n cocycle if, if n equals 1, then d rho is just a function on two variables, gh. This will be equal, this is just rho of g plus rho of h, or plus the g acting on rho of h minus rho of g plus h. And if we take the trivial action, then this would just be, to say that this is 0, this is just a homomorphism. Okay, so I'm just putting this in place with a question I asked before. Okay, so this is a trivial action and a true homomorphism, a true cocycle. Not an approximate one, it's just a homomorphism. Okay? And similarly, say that, so maybe we say that rho is a function from Gn to M. So we say that rho, which is a function from Gn to M, is n coboundary, n approximate coboundary. If there exists some cochain T from Gn minus 1 to M, such that the image of rho minus delta T is inside Mi for some I. Okay, so if this were equal to 0, this would be a true coboundary. To say that if rho is a coboundary, to say that it's the boundary of some other map, and this would be an approximate coboundary if I allow this to be in one of my filtration groups. So in the case n equals 1, then if n equals 1, then n minus 1 is 0, then these are just constant maps, and the boundary of a constant map is nothing. So this or 0. So this would just say, in the case of n equals 1, which is our case, this would just say that the image of rho is inside Mi, which would just say in our case this is a bounded rank. In my filtration, which is the filtration coming from rank on polynomials, this would just say that an approximate coboundary would be a function whose image is bounded on this Mi. Okay? Is the sort of the relation between this and this clear? I think this is a good formulation because then there's so many questions you can ask, and I can only answer one in a very special case. So now, okay, so you have so it's easy to see that these guys are the approximate cocycles and approximate coboundaries are groups. Okay, this is because of the filtration condition that Mi plus Mj is an Mi plus j, or it's constant times n plus j. So you can define this. So the group of approximate cocycles, this would be, we'll denote it by Zn tilde of Gn, and this would be the group of approximate coboundaries. This would be Bn, Gn, and there's a very natural map from, there's a natural map, there exists a map, A, from the regular cohomology, Gm. If something is a true cocycle or a true coboundary, then it's also an approximate cocycle and an approximate coboundary. So I have this natural map from Hn to Hn tilde M, which is Zn tilde mod Bn tilde, and the statement of this theorem, our theorem is that A is onto, under the conditions I said before. So I'm looking just at the trivial action. But you can ask this question, well, I don't know how to answer almost any other question about this. You can ask the questions, what about, so maybe I should say AN. So A1 is onto. That's the only one I can say. But what about A2? Or any other questions? I'm at this moment unable to say anything about these. Okay, Yeah, unless there is some hidden concept somewhere that I don't know, and somebody, I couldn't find anything about this thing in the, so there's lots of things in the literature about various things in the bounded cohomology, but I didn't see anything in this, of this type. But let me describe to you, okay, so this is, I'm back to my original question, just a formulation, I'm giving you lots of questions. Anything you want to ask here, I think is not known. There are lots of things you want to ask, you might want to understand, but back to this very basic question, this is kind of a matrix question, right? I have this map into this matrix group, I know that it satisfies this condition of almost homomorphism, I ask, is it close to, in this sense, close in this rank sense to a true homomorphism, and the way I want to describe to you how to prove that. So is the question clear in the...
That theorem is for every... Yeah.
No, A is on, of course not. But for G is this V, infinite dimensional vector space over P of prime field prime. And actually, and this filtration, MD, so okay, maybe I should state it correctly now. Let me state I forgot all kinds of things I should say. Thank you for asking. So MD is we come with this rank filtration and then I can show that A1 is onto, sorry? Yeah, homogeneous polynomial. And I can show that A is onto in the case where the P is greater than the degree minus 1. Thanks. Actually, very, very thanks. So I can't, this is yeah, there's some additional condition here. No, okay, there's just extra condition. A1 from, so any, yeah, A1. Well, actually, we can also calculate the kernel of this map, but I don't want to get into that now. Yeah. So you should ask me that later, and I have to think about it. It will take me some time to reformulate that in terms I feel comfortable with, and then I'm happy to try to answer. Okay? But it's not at all clear. Well, I don't, if the group G is Z, I don't even, well, okay. You asked something about this thing over here. Okay, tell me later, I'm happy to understand. Okay, but basically what I want to do is describe how to prove this. So how do you prove it? So the ingredients for proof. First ingredient is, well, I told you I only know how to solve this proof in algebraic means if I sort of in the rank 1 case, like if everything, then I can sort of run around, sort of follow the transformation around. But in higher rank, and for matrix, high rank, I don't know how to do this. So there's a nice way to, a nice interpretation of rank, or a way to see rank in an analytic way. So this comes through, I'll call this the bias implies low rank. So this is the first ingredient, and so I guess this is the theorem of Green and Tau, and in the high characteristic case, and Lovitz, Kaufman in characteristic 2, and also, not exactly this, what I want, but in the formulation that I need, it's actually Lovitz, and some, this guy, I want to spell his name correctly, B-H. And it says the following, so I'm going to fix my field K, it's going to be some FP, okay, so this is my prime field, and if the exponential sum, so I look at, so say, so I'm going to fix K to be FP, and now I want to think of V as a finite dimensional, so this is my group G, okay, this would be a finite dimensional vector space, G, my group G, and my V that's actually in both places, so everything is V, and V is a finite dimensional vector space over FP, but I want to think of a very high dimension, so later I just piece the solutions that I get in each dimension to a very high dimension. And this theorem says that in this context, if you look at the exponential sum, e to the px, you average over x in v, so fix a polynomial. Okay, so p is a fixed polynomial. And this e over here would be e of t is e to the 2 pi I t over p. If I look at this exponential sum, then if this is biased, if this is greater or equal than 1 over p to the s, then P is of rank that is smaller or equal than some constant depending on D and S. Okay, so if I have a polynomial P, if this is a quadratic polynomial, then you know, right? If this is a quadratic polynomial, then if the exponential sum here, this would be something like 1 over P to the rank of your, yeah.
What are D and S?
If I know, if the bias of this exponential sum is greater than 1 over P to the S, then P is of rank that depends. So D is fixed. I can think of D is fixed for the. I just wrote here that this D over here to say that these results over here were dependent on P, and this result over here is independent of P. So this is maybe the state of the art, I think. Okay, is it clear what the parameters of D is? This one is fixed in advance. I'm living in MD. MD is for me, or it's all polynomials of degree D. The rank is expressing polynomials of degree D in terms of sums of kind of products of lower degree polynomials. Okay.
Take any polynomial, basically this rank is large enough, which is very large enough. Good translation.
Okay, perfect. Well, I think it's the one I know, but okay. So maybe maybe it's known. Okay, I'm happy for any information. This is maybe 10 years old or something. So, or I don't know about the various improvements, but basically it tells you, okay, so if you have bias, then you have low rank or whatever H something invariant. So this is one ingredient. The second one is that actually there's a kind of a converse. So the second one is that if P is of rank smaller or equal than R, or so rank R, I can look at, and it's of degree D, so I can look at these derivatives, delta D1 through delta H1 through delta HD of P. This would be delta H of P at the point X would be P of X plus H minus P of X. So this would be a multilinear. This would be multilinear in H1 through HD. Okay, so P was a homogeneous polynomial in D variables, and a homogeneous polynomial degree D, and if I differentiate it D times, I get something which is multilinear in H1 through HD. And this is a if P is of rank R, then this exponential sum. So maybe this is easy. This is kind of a lemma, small lemma. So this I don't know if it has another. This is not so easy, but this is very easy. At least the proof I know that they have for this is not easy. Of e to the delta H1 through delta HD of P. If I average this, then this is biased by some constant depending on R. So if there's bias, then that implies low rank. In the other direction, if there is low rank, then not necessarily bias of polynomial P, but its multilinear version is biased, and actually without an absolute value, and that's kind of crucial. So this is very easy to show. But the third one, which is not, this is kind of the ingredient. This is what motivated me to think about this is the inverse theorem for the Galois norm over finite fields. So this is a result by Bertelsen, Pao, and myself, and other work of Pao and myself from actually the last time, the first time I was here at MSI. We were working on this, and it says the following. So these results are about polynomials of degree D. So if a polynomial of degree D is biased, has low rank, and if it's low rank, then its derivative is biased. This is a result about a general function. Give me any function f. If f is any function from V to say FP, say my field, and suppose I know that if I take this multilinear derivative, so if I differentiate it d times the same way I did over here. Okay, so I say, but this is a general function. It's no longer a polynomial. I know nothing about it. Okay, this is some any function f. If I differentiate it d times, and let me differentiate this e to the f of x d times. So I differentiate it into exponents. Okay, so this, if this thing is hope I did this right. Yeah. If I differentiate this and I average over x and h1 up to hd, then if this thing is biased, if this thing is greater than some delta, then I can't say that f is low rank or anything. It's not a polynomial of bounded degree, so it's just some function. But if the derivative is biased, if its d-folded derivative is biased, then my function f correlates with a true degree d polynomial. Then f correlates with a polynomial. Maybe I should write it precisely. F correlates with a function q, maybe e to the f, correlates with a function q that satisfies that delta h1 through delta hd of q is nil. Let me explain this. What correlates mean and what it's so this means that there's some constant depending on delta, maybe it's tilde, such that if I look at the average over f of x, e of f of x, q of x, damn it, that. Okay, so let me let me say that this is, okay, let me change it, and then in high characteristic this would be true. This thing, maybe not do that. Yeah, okay, I'm sorry. Yeah, sorry. I hope I'm saying this. I hope I'm doing this right. I have to think about it in a minute. But then there's a function q whose d-fold derivative is 1. So if I differentiate d times, I get 1. If the characteristic is higher than the c over here, then this is the same as a regular polynomial that we are used to. But otherwise, there are some other things that come up. So if p is greater than d, then just a polynomial. Q is just a polynomial. Okay, so correlates means that there exists something like this, where this is greater than c. Okay. In particular, what does this type of thing mean? Well, this is kind of, if I have any function f, okay? So I start out with a general function f. If I know that its d-fold derivative is biased, if I started with a polynomial of degree d, and its d-fold derivative is biased, then it's low rank, okay? If I start out with any function p, and I know that its d-derivative, d-folded derivative is biased, then I know that this exponential sum is, then there is some function, some true polynomial q where my function f correlates with q. Okay, and actually this was the motivation for it. I was trying to figure out a different proof for this thing over here. This is the question that interests me. and actually, if you can solve this other question by some other means, then that would give a new proof for this theorem. Currently, the proof of this thing goes through ergodic theory. There's a translation for ergodic theoretic question. There is a structure theorem in ergodic theory, and then pulling back the result to this finitary context. And yeah, you're asking.
Is here a finite dimensional vector?
Yeah, I said everything's going to be finite, and then later you can piece it all together to kind of a solution to the infinite dimension one. But you want to think of the whole thing as all these bounds, so V is finite dimensional, but all these bounds are independent of the dimension. Okay, so you think of the dimension as being, maybe I should have mentioned that. You think of the dimension as being large, very large, and all the bounds are independent of the dimension. Okay, so let me describe how to piece together these things. Actually, the idea is based on this idea of Green and Tau and independently Shakalovic, who were trying to show this equivalence between conjectures, the polynomial Ruja conjecture, whoever knows this, and some conjectures in additive combinatorics. And so it's related to ideas based on an idea from there. And what you want to look at is to look at the function. So I'm given reminding you where I am. I'm giving this function rho from V to polynomials, so this MD, so this would be polynomials of degree D. And I know that rho of G, for any G, rho of G is a polynomial of degree D. And I know that rho of G plus H minus rho G minus rho H, the rank of this guy is bounded by some uniform R. Okay, so again, I'm doing everything in the finite context, but you can think of all of my bounds are independent of dimension. Okay, so V is finite, so I can make these averages and whatever, but all the bounds that come up are always independent of the dimension of the vector space. So I have this condition. So look at the function. F of G, let me write it, H1 through HD, so which is equal to rho G of H1 through HD tilde, and this guy over here, so if I have a polynomial P, I will denote by P tilde, this will be the multilinear version. So this would be delta H1 through delta HD of P. Okay, so I need to go both ways. I need bias implies low rank, and low rank implies bias, and I only know low rank implies bias for this multilinear version, so I'm going to work with the multilinear version of my polynomial. So I take my polynomial P, and I look at its multilinear version, which is this guy over here, and I look at this function. This is a function on V times V to the D plus 1. Okay? And I can use, look, this position looks very much like a derivative. If you apply this thing kind of twice, then this thing is going to look like differentiating, like differentiating twice. So show that delta H1, not H1, delta G1 R1 up to delta GD plus 2. RD plus 2, I'll write it in a minute. I take this function, I differentiate it, well, for every space G, if I differentiate this function, this is a multilinear function of degree D. If I differentiate it D plus 1 times, it's going to die. Okay? Right? But my problem is how to relate it to this parameter G, which I know nothing about. Okay? G, this is a nice function, but I'm trying to kind of deduce this thing as kind of a linear behavior in this G. This would be a kind of a homomorphism. So I look at this, I take this function, I need to differentiate it sufficiently many times, so I differentiate it with respect to both parameters. Turns out that you do D plus 2 times, so this thing, E of S, this thing, which is the same as looking at the U D plus 2 Gowers norm of the function, this function was set on the group V to the D plus 1. So when you look at this thing, you use the fact that multilinear guys are biased to show that this thing is bounded away from 0. Okay? So you use this information and this information bounded rank implies bias to produce a function with a large U D plus 2 norm. Then you use the inverse theorem for the Gowers norm. So this is the first step. Second step is to use the inverse theorem for the Gowers norms. It would be use inverse theorem for the Gowers norms to conclude that this function f that I wrote before, that this function f, that f correlates with a polynomial, but this polynomial is in all the variables h1 through hd. It's a polynomial in d plus 1 variables. Okay, so it's a polynomial on v to the d plus 1. Okay, this is my new space. But you can use this. Then 3. From this information, you can deduce that since you already know linear, so you know that for any fixed g, you already know linear behavior. You have some information on this function f. You know that this function f, when you fix g, is a polynomial. This g is the only linearity you need to get on this g. So you can use this to show that to get this polynomial q, such that get that f of g, or not f, this original rho of g minus p of g, the rank of this is bounded for many g, for positive density g, number of g, and then propagate. And then 4 is use some basic steps in additive combinatorics to propagate using approximate co-cycle condition to all of g. Oh, B, G, V. Okay? Yeah. Okay. So. Right. So let me sort of recap what was interesting for me and what I was trying to do. So what was interesting to me is this question over here, a general question in polynomials. I have this polynomial. I have polynomials of degree d over a finite field, and they're over vector space and over a finite field, and they are filtered by rank. So I have this. I'm fixing the degree of the polynomials, and I'm interested in this rank filtration, and I'm giving some function into these polynomials, this group of polynomials that I know that is an almost homomorphism, an approximate homomorphism in terms of rank. I know that the rank is the homomorphism condition is satisfied for all pairs up to some given bounded rank. Okay, and I'm trying to find a homomorphism. I'm trying to show that my function is up to bounded rank, a true homomorphism. Okay, and the way I know how to do this, well, I don't know how to do this in any algebraic way, and I would really like to see some algebraic proof of this. If one can come up with an algebraic proof of this, then that would be